compute the commutator, A minus A plus, you get the following kind of what we call with U the Q lambda deformation. A minus U, A dagger, V minus one minus O1 over lambda, remember, is our number operator. Lambda plus 1 A dagger V A U minus is equal to UV times 1 over lambda plus 1. So you get an awful deformation of the standard Fock space with nothing to do with the usual Fock space. Okay? You see, why this remark is relevant? Because this remark comes, this isomorphism, it means that if I make the following isomorphism, I take homogeneous power n and particle space in the boson-Fock space over V. But this is standard boson V with the scalar product in V. Okay? And I associate to this the homogeneous tensor power in the homogeneous symmetric tensor power of V, because the homogeneous tensor power generates the symmetric tensor power of G, then this is unitary. Now, see, because the scalar product is the same. The scalar product here is equal to the scalar product here. It means that this map is unitary. Now, this scalar product is used standardly in quantum stochastic calculus. Because in quantum stochastic calculus, we define the exponential vectors with the square root normalization. Okay. So when you take the inner product of two exponential vectors with this normalization, well, you see here the tensor that you will find the tensor you will find that this scalar product which is equal to this. So you get the exponential series and you get the famous reproducing kernel property. Okay? So this gives you what we use in stochastic calculus. Now, but this convention with this isomorphism gives the wrong commutation relation. What are the correct commutation relations? The correct commutation relation comes from A minus. So let me write correct. Commutation relation will come by taking A minus U A daga Vn A daga V1 V to be just the sum, without any normalization. Just the sum from K1 to N of U Vj, and then the same A daga V N A daga Vj absent A daga V1 Then it's a very elementary calculation that you can do very easily, and you find that with this definition of annihilator, then you get as it is expected from the standard theory. Okay? But how about homogeneous tensor product? If you compute now with the new definition, you have A daga U A daga N V phi. Then you compute with this definition. So you see, all the V are equal, these are all equal, and you have N of them. So this will give N UV A daga N minus 1 V. See? Therefore, if you compute the same scalar product as we did before, that is A daga U N V A daga V V N V, then you bring this here and you get 1N U V, and you get the same scalar product but with N minus 1. Okay? So when you iterate, you don't get uv to the power n, but you get n factorial. Okay? But since you have this n factorial, it means you cannot define the exponential vector as we do in stochastic calculus, because you don't get the reproducing kernel. What you want is to define the exponential vector as the sum of n of 1 over n factorial v tensor power n. See? Because when you do the scalar product, you will have, using the orthogonality of n-particle spaces, you will have n factorial square here. And then here you will have the scalar product. Okay? in the usual tensor space. But now we know that with the new convention, the scalar product is n factorial. So this gives sum over n, 1 n factorial, because it simplifies, the square simplifies with the n factorial coming from the scalar product. You get again uv power n, and this is the correct reducing term. It means that if you use the definition of annihilator, you will find this correspondence. You will find that this is unitary, but the commutation relations are terrible, are deformation.
Why are you saying deformation? So I didn't understand why you're saying deformation. Deformation, you're using the term deformation.
Well, it's a long story. Usually in the literature,
so first I didn't understand which one is
many we now many years ago, some physicists introduced this deformation of interpolation of between Fermi and Bose. When Q is equal -1, you get Fermi, and when Q is equal +1, you get Bose commutation. And they were called the Q commutation relation. And in the years, they have been accumulated a huge literature on the Q commutation. Huge, absolutely huge. Now, with our theory of in one-dimensional case, we know that all these are, and in fact, it is not known, it is only proved. You see, when you define this, by the Fock prescription, the scalar product is uniquely defined. So, Q cannot be chosen arbitrarily. For example, it's very easy to check that the Q must be greater than, strictly greater than minus, cannot be strictly lower than -1. Otherwise you get a negative scalar product. But when the scalar product is positive, the proof of positivity was first given to my knowledge by Bozeko and Speicher in the late 90s, I don't remember when. And they proved only for Q less or equal than 1. Or even less than 1, I don't remember. But we have a lot of examples of deformations which depend on lambda, on the number operator. And these, in fact, we know that they are the standard, because if you remember well, we know that for every state phi on P, the polynomial algebra, with Jacobi principal coefficient omega n, the commutation relation are which by definition so you know that what we call with Lu the omega lambda commutation relation are absolutely universal. The choice of the Q commutation relation come when you take the Q equal -1 requires a little bit, because the space is finitely supported, is the Fermi space, is the Bernoulli measure. So the Q deformation is equivalent to take omega n equal Q n minus 1 over Q minus 1. See? So you know, this theory shows that this kind of phenomenological deformations that were studied in physics and without a theory underlying. Now we have an underlying theory that tells you precisely which will come up. But this is a digression. So you see, what I want to say, this normalization is very interesting because this is a stochastic calculus. Quantum stochastic calculus normalization. What is this normalization? This is white noise normalization. This is what they use in, and I always was wondering why there is this difference between white noise and stochastic calculus. Because they have the same space, the boson Fock space. But now we understand essentially is a question of which isomorphism to establish. They use this isomorphism. In stochastic calculus, we use this isomorphism, in which the symmetric operator go to the non-normalizer. But in white noise, they use this isomorphism, in which they use the same isomorphism, but with the correct this isomorphism is not compatible with the commutation relation. Okay? But if you take the correct commutation relation, the correct isomorphism should be if you want to obtain a unitary isomorphism, you have to associate to the n particle vector not the standard product but the rescaled product. If you do this, you get unitarity. So, you see, this was a very good remark because it allowed to clarify an old story that why two different communities use different normalization, you see. I think something still should be checked because, you see, if you fix the normalization, the commutator condition is purely inside the Fock space. But then we have the two isomorphisms, one with the canonical Wiener space and two of the Wiener space. And then we have the isomorphism with the usual definition of Fock space in terms of symmetric tensor product. So I think a small control should be done if this is compatible with if the correct commutation relations, which are these ones, the correct commutation relations, which are this one, and which give not this isomorphism, but this isomorphism, are compatible with the isomorphism between the Fock space and the L2 Wiener space, because that is fixed by the martingales, exponential martingales. So this is a control that should be done, because otherwise we have to change a lot of estimates in quantum stochastic calculus. See? Okay, I think now